It's a high-tech conversation.
And a low-tech topic.
Live on the World Wide Web via Zoom. Bench Talk 101.
Good evening, everyone. Welcome to Bench Talk 101. It's my pleasure to introduce, well, I won't be doing the introduction, Jim will in a moment, but it's a pleasure to welcome Boaz Zeffertt to come and speak to us tonight. So over to you, Jim, to, I guess, to introduce Boaz.
Thanks, mate. Thanks. Welcome to Bench Talk this evening. It's a rather different genre tonight, and we're always trying to push boundaries as to unique and different crafts that we feature, and Boaz Zeffertt is definitely going to be one of those. I've known Boaz for quite some years now. I'm not quite sure how many, and we won't talk about that, Boaz, but somebody mentioned tonight, Steve, I think, that we're now blood brothers because I managed to cut myself on his blade tonight. But anyway, when I first met Boaz, he was featuring, I think it was on Instagram, as quite a few beautiful little infill planes that he was making at the time. And I was running the Richard Arnold charity auction, I believe it was 2017. And asking for donations, and Boaz put his hand up and said, "Hey, look, I'll send you one of my planes," which I believe is now with our very own Chester Spear in America. So fabulous plane, and it fetched quite a lot of money. So that was my first introduction. Over many years, I've been interested in metallurgy and particular laminated plane irons from Sheffield. And I got into conversation with Boaz when he started a different tack in his craftsmanship and started up a forge up in the mountains in South Africa. And basically I said to him, look, how do you fancy getting yourself involved in forge welding and making laminated Sheffield irons? So the conversation went from there, and he sent me a sample which I have here, and it was so beautiful. The iron itself was absolutely wonderful that I said to him, I need to make a plane around it suitable for it, and that's how we're up to date now. And so I said to Boaz, and Shrenick agreed with me, that wouldn't it be great to get him to come on as an invited guest to talk about his processes and some of the things he makes. And it's not just plain irons. I've seen some scorps being made. So this craftsmanship extends across the range of tools. And I'm sure anything that was originally forge welded would have been is possible and is becoming possible by the work that Boaz is doing. I know Rusty's itching to give an example. I'm hoping to see that in the question time. So without further ado, I'd like to pass you over to Boaz Zeffertt down in South Africa.
Thanks so much, Jim. Thanks everyone for having me. I'm going to share a presentation with you. Bear with me. Play. Okay. Fire welding is the technique of joining iron. It basically set off the Iron Age, enabling ancient man to join iron bloom into a homogeneous piece that was then usable. The materials coming from the iron bloom after the first round of fire welding would have been wrought iron, which is almost pure iron with some slag containing silica and phosphorus and sulfur. Wrought iron was the iron of sort of pre-1850s. Everything was made out of wrought iron to some extent. Every bit of metalware, from cookware, houseware, architectural iron, engineering iron, all of it. You can see in this photo, this is the end grain of a piece of wrought iron. that has been etched, and it shows the actual bands of iron with the slag in it. I forge in a coal forge. I find coal is just the most efficient source of heat that I have on hand. It's much cheaper than gas, like propane, and it gets much hotter, much quicker. The forge has an air blower that forces air in under the coals, and that passes through a water-cooled 2-air or 2-iron, which the water is necessary to keep it from actually burning away in the heat of the coals. The coal I use is bituminous coal, which is a medium intermediary grade of coal, and it has not been coked yet. It contains bitumen and other sort of fumes that come off it. I keep the coal wet as I'm burning it, and when I pile it onto the fire, the moisture and the heat coke the coal before it actually takes fire. So there's different layers in the fire, which are at the bottom a bit of clinker, which is the coal ash, not much. Then there's the layer of coke, which has coked, and then on top always the layer of green coal. At first it smokes a lot, but the minute it stops smoking, it's actually usable. In the process of fire welding, a very clean fire is necessary. And so from the point of lighting the fire, you have about 5 to 10 minutes to get all the smoke gone, get your coal coked before you can put your iron in and bring it up to welding temperature. The materials I use most often will be wrought iron that I scrounge from scrap metal, either from scrap yards or wherever it can be found. This is a piece of old wagon wheel, and you can see how uneven it is compared to a piece of modern steel. So the first order of business would be to take the wrought iron, heat it up, and get a relatively even bar, even in thickness and width. And it has to still be oversized, over thick to the final iron, because a lot will be lost in the heating to scaling. Here you can see the cross section. A bit difficult to this screen. The cross section of the wagon wheel. As you can see, this wagon wheel is uneven. The one side is like 1/2 inch thick, and the other side maybe close on 1/4. So it all has to be worked down, either cut a piece off and draw it out into a nice rectangular bar, more usable. I find cut the iron hot, as much hot work as possible. It saves time grinding and anything like that. So I heat up the iron and I have a guillotine, which I just crop it off with. Once you have a piece of iron that is sort of roughly the shape of the iron that you want, this is all done by hand and eye. I don't really measure much. It's all by feel and by eye. So I judge if I want an inch wide iron, I sort of forge a piece of 1 1/4 inch or so by a little bit thicker than what's necessary. Now, to accomplish a good weld in a fire, the surfaces have to be completely free of any kind of oxide, scale, debris. and any kind of oils, they really have to be clean. So I just use a grinder and knock off a bit of scale. You can file it, you can sand it, just clean it off. And then in this image, you can see there's the hard bit of steel laid on top of the iron, and there's a mild scarf cut into the edge of the hard steel. And as you heat it up and hammer it down, this prevents a cold shut from forming at that intersection of the steel and the iron. If the steel is left square there, it just sinks down into the iron and it leaves a cold sort of crack, which is really not desirable. So this scarf is an important step in getting it all even and smooth. Iron and steel have got very different properties in that the carbon in the steel affects the welding temperature. So high carbon steel has got a much lower welding temperature than the iron. The iron is welded at almost white heat, while the carbon steel is sort of a bright orange, almost yellow. And to get the dissimilar materials to a uniform heat that they actually stick is the trick. If I was welding two blocks of iron together, it would be a bit simpler in that you just heat it up to a very hot temperature and hammer it together, and the same for pieces of tool steel, sort of a much lower temperature. Joining the dissimilar materials takes a bit of trial and error in actually achieving the lowest possible fusion point for them. Overheating this billet would basically ruin the hard steel, it would burn it. And not heating it enough, it just would not stick to the iron, and the iron can also crack if forged under low temperatures. Borax is used as a flux, and I believe there's more than one use to the borax. First of all, it keeps the borax keeps the oxide layers from hardening inside the laminated joint and allows it to flow out as a liquid. When the fire is prepared and stopped smoking, you insert the bundle of iron and steel into the fire. When it gets to this red heat, dull red, you can add some flux. The flux keeps the oxides in a molten state and also possibly allows you to raise the temperature of the steel to a certain point because there's less oxygen around it. But it's mostly to help squeeze all the slag out of the weld. Once it's fluxed, you insert it into your fire and slowly bring it up to an even welding temperature. Both pieces have to be at a pretty much exact same temperature. And this is all, again, done by eye. There's no measuring with any kind of equipment. It's all by practice. You have to recognize the colors as the temperatures. I really don't know the exact temperatures, but I know the colors. And there's also a slight vibrational feel to the steel when it hits a certain point in the heating. And one just knows when the right time is. I suppose it's all visual with practice. It's hard to capture the colors of the iron at the welding temperature. It's never accurate. When heating it up, you have to have the visual aid of actually knowing what temperature your piece is in the fire. So pulling it out is in order. Pull it out once or twice while heating it and examine it quickly. When it's ready, you pull it out and you step to the anvil. With a few quick blows, you set the scarf end and then work your way down the center of the hard steel and then along the edges. It cools down quickly and you have to work fast, but not unnecessarily hastily. It has to come right almost on the first time. I'll usually take sort of 2 to 3 heats just to make sure that the weld is completely set. And the minute I start forging down the sides, if there's any sort of defect or bubble, it quickly shows up, and that's that. So you know when it's welded because you can actually see that there's no movement when forging it further. I do sometimes use a power hammer. This is my workshop, and it just means that I only have to take 1 heat and bang, and it's done. This helps from the point of view of decarburizing the steel, losing carbon to the heat. Every time you heat it up, it sort of diffuses into the air and into the iron. So the less heats I can get it to stick properly, the better. And this helps. But for small irons, it's completely possible. Just do it on the anvil. I'd say up to about 3 heats to get 2 to 3 heats would be the maximum for me to make sure the weld is done. Once the weld is done, you can't tell where's the hard and where's the soft. It's just, you have to actually mark it somewhere else and remember where it is. Because from here, one draws it out to size. At this point, it's quite a bit thicker and wider than the final iron. And so often I'll do a quick, I'll grind the scale off and just dip it in some acid and actually visually inspect the weld lines, the seams all around, and make sure that I'm on the correct side before stamping. While practicing these welds, I've taken apart many of them. I've chiseled at them, I've hacksawed them apart to inspect the welded surfaces. And generally the pieces that continue to forge as one piece without blowing open and bubbling are the ones that have no sort of inclusions when they cut open. It's very obvious when something's gone wrong when one starts forging it out afterwards. The shaping is it's almost always forged. One can grind, but that's sort of defeats the purpose because the forging is that much quicker, and because it's stretching the metal, you get to save material, and it just goes that much further. Drawing a taper is simply a matter of hammering in a certain direction, and then running a flatter tool over it to take the hammer marks out. Again, it's almost entirely done by eye, no measurements. Now and then I'll use a caliper just to make sure my widths are running parallel, but generally at this point it's all by eye. It's still rough. I want to go back to no. Okay, now normalizing and annealing. Very important, as quenching this steel is not easy. It's the one side hard and the one side soft is like sort of a recipe for disaster when it comes to quenching. A lot of other laminated blades, such as knife blades that one sees, which are laminated hard steel in the center and soft down the edges on each side, sort of counteracts the pull. When you quench a blade like this, if it's not completely normalized, the hard steel shrinks while the soft steel sort of carries on moving a bit as it's quenched. The hard steel shrinks and freezes in that position, and the soft steel shrinks and then expands a bit, which makes it banana. And it always becomes concave on the soft side, convex on the hard side, which is the opposite of what makes it easy to then grind out. So normalizing, which is bringing it up to the critical temperature and slowly letting it air cool, is incredibly important in this sort of blade to be able to quench it and maintain any kind of flatness. It really curves a lot. It can curve like 6 millimeters in the center over maybe 200 millimeter length blade. Getting down to heat treating. The heat treating, I prevent, one has to then bring the blade obviously back up to a much similar temperature to the normalization. It's again done by eye. So I'm judging the color in my workspace, which I sort of know what happens. This does limit the types of steel that I can use, because some steels just require that much more of a steady heat. To prevent decarb, which is carbon loss into the air during that last heat, because at this point I've already ground the blade to the final dimensions. I coat it in clay and a bit of charcoal mixture. Sometimes I mix a bit of borax powder into there and some alumina. This is just a very fine slip. It just keeps the oxygen off the face of the blade. And yeah, it all pops off when I quench it. So now I bring it up to temperature. Sometimes I check it with a magnet. Usually I'm just judging the temperature by eye, colors. And then depending on the steel used, I'll quench it in water or oil. For the laminated blades, tempering is almost not necessary, although I do believe it makes a better blade. It can be sharpened on a harder stone and doesn't require a completely friable, soft sharpening medium. So I just very lightly temper it. A laminated blade, I would almost like when you can barely see the straw color. Again, I don't know the temperatures because I'm doing it by eye. I temper over a gas flame, sometimes with a gas torch. I'll start at the back and do a drawn out temper. I'll let the heat sort of creep up to the edge, but I leave the whole half the blade or so almost untempered. It's just for sharpening really that the tempering is essential. It's not so much for chipping. After welding to the iron, obviously some of the carbon has migrated, and it's not only the carbon that determines the hardness, but for some reason they don't chip as readily as a solid piece of steel. In learning to weld, and even while welding, once one has a known process, there are failures. generally failures come down to either not being able to bring the piece up to welding temperature, a hot enough temperature, or having some dirt in there, or just letting it cool down too much before getting it to the anvil and hammering it. Between the fire, too much lag between the fire and the anvil. Like I say, these defects will instantly show up the minute you hit it on the side. It pops open. I wouldn't attempt to re-weld something like this. For me, it's scrapped. I know some people do, but it's yeah, that's that. I believe these laminated blades are not the best, finest blades in the world today, but I do believe from a historical perspective, they very much existed and fulfilled their roles brilliantly. And therefore, I really do think they have a place today amongst all the modern tool steels. There really is a place for these. They are completely usable. The reasons for laminating these historically was obviously a function of saving material costs, which today is not really relevant, as wonderful steels have been developed and they are much more affordable. Any questions? I'd be happy to discuss any of these points if I didn't elaborate enough on anything. If there's anything to go into detail.
Thanks, Boaz. Thanks for a brilliant talk. I'm just gonna stop your screen share for a moment, just so we can see people when you talk, and you can pull it back up if anyone's got any questions and you want to show a picture. So you delivered an amazing talk, and I know that there's loads of questions already flowing in. So as always, if you pop your name in the chat, we'll give you a chance to ask Boaz a question. I'm going to ask everyone to keep it to one question this week, and if we've got time, you can come back to more questions. So Paul, about 1 minute into your presentation, popped his name down to ask you a question.
I wanted to go first.
Yeah, well, you did very well at that. So over to you, Paul.
Thanks for absolutely superb presentation. The question which I've got is the laminated blades. You sort of said that you temper them so that you can sharpen them on the harder stone.
Yes.
What do you actually use? What do you sharpen on and hone on?
So at first I'll be grinding them on a mechanized grinder for faster stock removal, and then I'll either use just abrasive, or I'll use water stones. I have natural stones, diamond stones, but the harder the steel, I find the more friable the stone has to be. Otherwise it does chip. If I don't temper them at all, diamond plates just chip the edges, and it's difficult. So a very, very mild temper, all it does is for sharpening, it reduces that edge fracturing. On a solid steel blade, I would temper to a more darker straw. Still lightly tempered, but a bit more.
Does it block up the diamond plates with the lamination?
No, well, no. On natural stones, I find that the iron actually grabs up particles and keeps it sort of refreshing the surface. The diamond stone, it doesn't clog. There is more sort of material because it's cutting faster, possibly, if you're sharpening the whole bevel.
Okay, thank you very much.
Thank you, Paul. I'm going to add Matthias.
Yes, thank you ever so much, Boaz. That was absolutely fascinating, not least from a personal point of view. My grandfather was a blacksmith, so there were some familiar images there. I wanted to, you actually sort of halfway answered my question already with your last few words about the shall we say, the value of laminated blades as compared to modern tool steel blades or all steel blades, and also, yes, obviously what we usually read about the laminated blades, that the technique was used to save on the more expensive steel. I suppose these days it's actually would be the labor in welding that would make it more expensive to have a welded blade rather than a full steel blade. But could you expand a bit more on shall we say, the relative merits and what are the strengths, or if there are any interesting points from the point of using the blade when it comes to a laminated one?
Yes, definitely. I think the foremost benefit of a laminated blade is the ease of sharpening, which is for me always been quite a major issue. I don't enjoy sharpening really, really hard steels, and that to me is the biggest number one benefit. After that, there's in making them, it's so much more interesting to me than just actually sawing out a block of steel.
Yeah.
But as to the benefits, I don't know if there's more shock absorption, or I think ease of sharpening is ultimately the number one benefit. Yeah.
Yeah, it makes sense. If most of the primary bevel is softer, because indeed, yes, when one has to regrind the entire bevel in one of those modern steels, if you do it by hand, you're in for a couple of happy hours. Yeah, been there, done that. Thank you very much.
Thank you.
Thanks, Matthias. I believe we're on to Chester.
Hello, Boaz. How are you?
Hey, Chester, how's it going?
Very good. I wanted to point out that this is the plane that I got at the auction from you, and it's got this incredible throat here. And it's one of my favorite planes to use. And I run in here often whenever I have some little figured wood or something to use this on. So I want to praise you because it's probably one of my favorite planes of all that I have. My question to you is when you're hammering the steel to the wrought iron, how do you control the depth of thickness? Do you grind off of the wrought iron side to make sure that the two are at the right level between the two where they're laminated, so that you have enough of the steel to grind? Do you know what I mean?
Yeah, I start with a ratio of much more iron on the billet than steel. So it'll be about 6 millimeters or 10 millimeters of iron to 2 or 3 millimeters of steel to begin with. And as it forges down, the ratio sort of remains a quarter to a third of steel. If there's too much towards the end of steel or of iron, I can grind off and adjust or draw it out depending on which side I hammer it on.
Gotcha.
It'll stretch out thinner.
Well, you do wonderful work. Thank you for the presentation.
Thanks so much, man.
Thank you, Chester. We're on to Jim. Jim did enough of an intro. He still has a question for you.
I do, because I'm allowed to, you see. I'm allowed to actually,
Yeah,
you know,
I need to change the rules here.
For the second week in a row, I know intimately most of the details of the person I'm speaking to. So it's sometimes difficult for me to imagine that I would have a question, but I do. And the question came to light with your slurry, your decarburization slurry on the final stages of hardening. I encountered the idea of preventing any loss of carbon from any part of the steel when I made a float of it was just 01 steel, but because inherently a float is difficult to make without the edges being sharp to the final state. Yeah, I had to make a slurry of, and I looked through many things and found that mixing borax with water and then coating it as a paint and everything, my resultant quenching exploded quite dramatically. It was like burning flames and things like everywhere. I was interested in the composition that you mentioned. For a start, your slurry was far thinner than mine. Mine looked like it was one of those chili dogs that was dipped in. But yours looked like it was beautifully applied to the steel and very thinly. What constituent parts, what ingredients is it a secret? Do you use to make that paint that you put over there to prevent that decarburization?
It's basically even almost equal parts of clay, sort of natural clay that I find on the property that I crush up into even finer. The clay I actually soak in water and sort of harvest the clay out of it, and then I take a fire brick and crush that up for the alumina, very fine powder, mix that in almost 1-to-1 with the clay, and then also charcoal, wood charcoal, crush that up and mix it in there, and then sort of keep that wet and dilute it into a very thin slurry. I think with the clay mixture, if it's too thick, it can prevent the quench from taking hold, taking effect on the steel. It actually blocks the cooling. So it has to be a really thin level. And the reason I put it right down the face is that I've ground it already flat and fairly fine grit, and I want to preserve that surface. And it's not, this mixture, not very explosive, I must say, going into oil or water. It all flakes off the minute it goes in, but it doesn't pop.
No, because it's particularly thin. I mean, that's where I made the mistake. I mean, my one worked. It quenched quite well, very well, because my float works perfectly. But it obviously was too thick, and it's a bit of a eureka moment, me seeing your. And also, it's fabulous that you're getting that clay and you're not buying it on Amazon, and you're just going out into the garden or the hillside and picking up the clay and doing it yourself. That's fantastic. That has solved a lot of future problems for me in terms of my work on my minimal work on hardening that I do on tools, and I look forward to. I don't know if I'll be able to get all the bits that you get out in the Veld, but I'll have a look and see what we got in London. I think we've got some clay up there somewhere. So thanks very much for that. It was a bit of a mystic. You can't find that information anywhere, and it was very helpful. Thanks for that, mate, and thanks for a wonderful presentation, as I expected it to be.
Thank you so much.
Thanks, Jim. We're on to Mitch.
Hi, Boaz. Thanks for a very interesting talk.
Hello.
I was hoping you might explain what the sort of minimum thickness of the steel would be for the best application. Presumably for speed of sharpening, it wants to be as thin as possible, but obviously there must be a minimum that is effective.
Yeah, I'd say in millimeters, the final, if the final, I'd say around about 1.5 to 2 millimeters. 2 millimeters being on the thicker side for a thicker iron.
Is that helping to give the iron more rigidity in itself as well as being the sharpness?
It does, but you actually just need a certain amount of thickness to apply a bevel to, I think is the most important part. It can't be paper thin because you just can't get a bevel onto it.
Okay. And how accurate do you, when you're actually forging it, how accurate can you get with your thicknesses? I mean, how much do you need to grind away at the end of the day?
Not much grinding. If you start out with the correct ratio of steel to iron, if I start out with a 3mm sheet of steel that I buy, hard high carbon steel, I'll aim to forge the iron blank into roughly about 10mm. So it's about 3 times more iron before welding than steel.
Okay,
then,
thanks.
Yeah.
Thanks very much. That's very interesting. Cheers.
Thanks.
Thank you, Mitch. We're on to Rusty.
Hey, Boaz.
Hey, man.
Good to see you. Hey, I want to ask you about this knife that you made that I have. Can you talk a little bit about the process that goes into this? I'm guessing it's not the same as what you were describing today.
So it's a very similar process, except for those are 2 different types of high carbon steel. And it just means that the welding temperature is much more similar in general than the dissimilar iron and steel. Other than that, it's pretty much all the same, the actual process. It's made up of much more layers initially. I don't remember exactly how many that was, but for example, 10 layers to start with of alternating metals.
So you start with those 10 layers and then you just thin them down as a draw it out, or you fold it over and over again?
So one way you could have a lower layer count and just get that weld set and use it as is, or draw it out, stretch it, and then stack it up or fold it and just keep increasing the layers exponentially like that.
Excellent. It's a pleasure to use. It's very different. You know, in shape, it's very similar to what the Japanese grafting knives are like.
Huh.
And that's what I use it for. I don't actually use it as a marking knife. I use it for bonsai.
So cool.
But yeah, it's a really special tool. Anyway, thanks. Good to see you, man.
Awesome.
Thanks, Rusty. I think we're on to Stephen. Just need to find him. There we go. Add spotlight.
Here we go.
Stephen.
I loved your presentation. I do period carpentry of the 1830, 1840s period at Sutter's Fort State Historic Park, and we have a full operational blacksmith shop. And so you're doing exactly what we're doing. We're for our wrought iron, we usually go for car springs, but the cars have to be before roughly 1960. So you go back. That's one of our sources when we're doing forge welding. But I really enjoyed your process, because you're right. It's hard to explain the fact that it is the color of the iron when heated. And you can only get that from failures.
Yeah.
It's basic. That's, you know, that's why you start as an apprentice and you work a lot of time. And that's also the reason why blacksmith shops are also dark.
Mm-hmm.
Because you need to see that iron color to get to that point where you need to have for whichever process you're doing. I was just wondering, do you just you used a wagon wheel. I was wondering, do you do any folding of that to get some alignment of the wrought iron fibers before you throw this the hard the hard steel on top of it, or do you just use it as is?
That will depend on the quality of the iron. As I get it is usually completely rusted, and as I forge it down into bars, it sort of reveals itself. And if it's really low quality, I will stack it up and make a layered billet out of it. It's also possible to then control the actual pattern in the grain, but generally I've been quite lucky and found fairly high quality iron. Sorry. It mostly all that I find or get is is from wagons, which have played a major part of the history in South Africa, right?
Right.
The beginning of the European arrival. And the iron comes from England. It was forged especially by companies like Rigby's and a few others for the South African ox wagon. So there's axles, which are really big sections, like 3 by 3 inch, really heavy duty axles, and then all the trim and the tires. And as these wagons traveled up the country and in the Great Trek, they were sort of abandoned on farms along the way and used as fencing poles, and the people that restore them just have so many used up parts that they'll never be put back onto a wagon. So I think it's a cool way of using it. And like, yeah, it's usually a fairly decent quality iron that doesn't need to be done much other than just straightened out.
Now, in our case, we are dealing with, we're the terminus of the great gold rush trade coming to California. And so we get the old and broken down stuff, but so much of that is being hoarded in museums and so on, that we didn't have a lot of sources. So for the want of looking for good iron is the leaf springs in the old automobiles were a good low-cost source for wrought iron.
It's interesting. Scrapping has become quite a passion of mine, I guess, and a few of my friends. And it's good to know where to look for these materials because they're just not available otherwise.
Yeah, it's not something you can go down to your local steel and iron purveyor and get. It's usually the scrapyard.
Yeah.
So I'm good. Thank you very much. Great presentation.
Thanks, Stephen.
All right, I guess my turn. Hey, Boaz, great talk. Thanks. You touched on, and then also Stephen touched on kind of my question multiple times. I've thought about getting or trying some of this, but I'm colorblind. And you always talk about how you can tell the temperature by the color. I can see colors, I just can't tell you what it is. You know, like I'm not black and white colorblind. If you couldn't use color, could you forge metal? Like, do you think it could be done, or could you learn? Like, is it a...
There are some surface, how the surface of the actual metal looks during different color stages that could potentially be a way to do it. I think you'd need somebody who can see the colors initially to be with you and sort of decide on what it looks like at a certain color without using
the other colorblind guy in the entire world can get him to teach me. The one other guy. No, yeah, that's kind of always been what's held me back. Is like, well, looks yellow-ish. So, you
know, at the forging temperature, it starts at a sort of dull cherry red, and at that point there's usually not much scale formation yet, so it still looks fairly smooth. And as you increase the temperature, the scale will inevitably start forming on the surface and look slightly different. And then at much higher welding temperatures, the steel welding temperatures, it starts looking wet. You get a sort of a glisten on the surface of the steel, and then at the white heat, it looks molten almost.
Yeah.
So I suppose there could be other visual indicators. It's very interesting. I've never considered color blindness as an issue. Yeah.
Okay, so next time you go out, wear some yellow glasses or something so all your colors are off, and give it a try.
Yeah, man.
All right, thank you.
Thank you.
Thanks, Rick. On to Ian.
Hi, Boaz. Thank you very much for all of that. My sort of crude knowledge of steels and iron, that iron has roughly a 4% carbon content and a high carbon steel has less than 1%. I just sort of intrigued, or if you knew how historically the steels that were welded on before the 1850s, how were they created?
From what I understand, it was the lower carbon wrought iron, which would then be carburized, soaked in a carbon-rich environment for some time, overnight, over days, until it actually soaked up enough carbon to be made to harden. Cast iron is a different, that's very high carbon, which can't really be forged. It just starts crumbling.
Right. So wrought iron, that what sort of carbon content is old wrought iron then?
Almost no carbon.
Oh, right, right. Oh, I didn't realize that. Yeah.
It's got almost no carbon content whatsoever.
Right, right. So you're adding some carbon to the wrought iron to get the high carbon steel, as it were.
From what I understand, I'm not 100% knowledgeable about the actual production methods.
Yeah, sure.
Of these old steels, but from what I understand, that would have been, I believe, if I'm not mistaken, blister steel.
Right. It's not a term I've heard.
And then the famous cast steel, which is stamped on the old iron from Sheffield, is actually iron and possibly some alloying elements that were molten cast and then formed into these strips and then welded onto the lower carbon.
Right, right. Right. Thanks a lot. Thank you.
Thanks.
Thanks, Ian. I think we've had another question come through from Bruce. Whoops. What am I doing? There you go.
Hey, man. Years ago, it was suggested to me that with laminated blades, if the lamination line is slightly wavy versus straight, that was a sign that the blacksmith worked the blade more and might be a better blade. Do you have an opinion on that?
There is a few ways in manipulating that line. If I weld it under the power hammer, under the dies, and it's just one shot, it remains two flat pieces, just snap together instantly. And if one hammers it with a hand hammer and along the side of the anvil to draw it out and imperfections come out, if you grind through those imperfections to make it all flat, there will be then almost those same imperfections mirrored in the line as the wave, you know. The hand marks will be translated from the face down into the. I don't know if it affects the quality. It probably has been worked a bit more. To me, the less I work it, the better it is at the end. It just getting them to that welding temperature too much really changes the steel completely.
Sure.
And so I don't know if the wavy line would mean higher quality.
Okay, all right, thank you.
I can't tell one way or another.
Okay, cool, thanks.
Thanks, Bruce. I'm going to slip in a question myself here. So, Boaz, you delivered a brilliant talk. You've answered some brilliant questions. But tell us your story. How did you actually get into smithing? And
so making planes for a few years before that, and trying to make my own blades and sort of succeeding. I wanted to really go a bit further in that direction of making my own blades. didn't really enjoy outsourcing the hardening process to an industrial hardener. And my neighbor happened to be this really talented blacksmith who happened to be looking for an apprentice, and I happened to be looking for an apprenticeship. And 3 years later, it was successful. And yeah, it's just how it's been. He was trained in England under some well-known masters, and he's passed all the knowledge onto me, and I've been incredibly grateful for that. But
It's great to hear that you've been able to come here and share some of that knowledge as well.
Thank you.
So it sounded like you were fiddling with a bit of metal there.
Yeah, I've got
You've got something to show us.
Not really to show. It's just my fidget.
Okay. Well, I had one other question, and I think Scott's going to poke his head up and maybe see this. Have you heard of Mokumi Gane?
Yeah. I actually successfully managed to make my first bit a few weeks ago.
How did it go? Did it go well?
I had many failed attempts, and like finally it worked. It's a tricky one. The copper and other non-ferrous materials are really different.
Do you think you could make a plane iron from it and laminate on some tool steel?
Like non-ferrous laminated onto the ferrous.
Yeah.
I've seen people doing it. I'm not there yet.
Okay. So it's possible. My question was, is it possible?
I think it is possible, yeah.
Okay. Well, thank you very much, Boaz, for a brilliant talk today. And in traditional bench talk fashion, as we've been doing for the last 18 months or so, we'll raise a glass and say thank you to Boaz, and cheers to the bench.
Boaz on the bench.
Boaz on the bench. Thank you.
Boaz on the bench.